All right. So let's start with some announcements here. There's a lot going on this week. There's everything. There's always a lot going on every week. So maybe just more so as we get into April. So homework 10 is due before class on Friday. And if you look at that assignment, you'll notice it's got the answers to the problems. It doesn't have the solution, but it's got the answers. So at least that gives you some idea if you're headed on the right track. Then we're going to have exam 2 in class on Friday. That covers just the open channel material that we've been talking about since we finished closed conduit flow. So that's classes 20 through 30. I'll provide the equation sheet. I'll have to get back to you, but I don't think there's anything that we'd use Excel for on the exam. I don't think you're going to necessarily need your computer, but I'll cover some more information about the exam on Wednesday just to be sure. You don't need to prepare an equation sheet because I'm going to provide the equation sheet. We'll be using that same one that's posted online. And then the reservoir sizing draft submission is due on Wednesday the 9th. And we'll talk briefly about the method for that today. And all you need to submit for Design Project Phase 2 is an Excel spreadsheet. There's no write-up, there's no hand calculations, just an Excel spreadsheet. And not the PDF file, make it the Excel file so I can actually look at the formulas. Okay, so does anybody have any schedule-related questions? All right, we're in the home stretch for sure. Class 29, I think we get to 43. I think 43 is the last lecture of the semester. So we're getting there. Let's talk about the reservoir. You've just turned in your draft submission for the pipe sizing, right? So I'm interested to look at that. I've given feedback to everybody on the demand estimation at this point. So if you haven't already, I'm not sure what kind of student experience it is. Like when I give you feedback, I don't know if that pops up in an obvious way, but I've written quite a lot of detailed feedback for everybody's demand estimation. And it's the final submission where I want to see the results of your improvements. So I will go in and I'll look at what I told you was wrong with your demand estimation, and then I'll look at your final submission to see if you corrected it. And if you did, then that's awesome. I'll be glad to give you a full credit on that portion of the project. But if I told you something was wrong and you didn't fix it, then I'll get pretty irritated. So definitely try and close the loop and improve your demand estimation if there are shortcomings. So you've done the demand estimation, got the feedback. You've done the pipe sizing. I'm going to be looking at that this week. Next on your to-do list for the project is figuring out how big does the reservoir need to be. In Phase 2, which you've just finished, you decided where, the location of the reservoir, and by that I mean what its elevation ought to be in order to pressurize the pipe network. But the size of it is also an important factor that's going to influence the overall project cost. In the cost data, I told you some details related to understanding how much it's going to cost. So the purpose of the reservoir is to provide pressure in the network. We've already kind of seen that in Phase 2, but also the reservoir exists to provide sufficient flow to the pipe network so that during peak times there's plenty of water available. And what we assume is that water is coming into the reservoir at a steady flow rate. And that's actually a pretty good assumption, whether the water is coming from a groundwater source like a spring or a well, or if the water's coming from surface water that's being treated in a water treatment plant. Either way, it's most efficient for that water production to be at a steady flow rate through the daily cycle. But human demand for water varies a lot during the 24-hour cycle. And so the purpose of the reservoir is to kind of act as a shock absorber or a cushion so that we've got this big supply of finished water ready to be used when it's needed. And so the question is, how big should the tank be? And to answer that question, we have to go back to this figure which you worked on for one of your homework assignments. What you did is you digitized that curve. For every hour of the day, you told me what was the percent of peak for that hour. And from that, we could assume some average daily flow. And in fact, you know the average daily flow from your demand estimation. You know is the peak flow rate. You know that bottom cell in the summary page, that design flow rate for the whole network, you're assuming that that is the peak of this curve. And so then if that's the peak of the curve and you have a data table that looks like this, then you can assign a flow rate to every hour of the day. So maybe your network was 500 liters per second. So 500 liters per second is the demand at 7 and 8 p.m. And so then the flow rate that's demanded by your network at midnight would be 36% of 500 liters per second. And so hour by hour, you know the flow rate out of the reservoir. And the flow rate into the reservoir, we'll assume, is the average of the outflows. And that's necessary. Otherwise, the reservoir is going to overfill if we have too much flow coming into the reservoir compared to what goes out. Or we'd run out of water in the reservoir if you're not having the flow rate in being large enough. So by definition, we're saying that the flow rate into the reservoir is just the average of the daily outflows over time. So an important concept that you really need to understand is look at the difference between this blue line, which represents our average daily flow, and then the area between the blue line and your flow demand curve. So at night, people don't use very much water. So at night, this reservoir is filling up. And then during the day, when people are using a lot of water, the reservoir is emptying because the previously stored water is being drained when the flow demand is greater than the flow into the reservoir. So the blue line represents the flow into the reservoir, the black line represents the flow out, and the area under the curve is a volume. So that's what you're going to do in this process, is you're going to figure out what is the maximum amount of water that's stored during the day, like how full does the reservoir get, in order to ensure that enough water is always available to meet the needs of the city. So there's a video here. It's a demo that I recorded a while back that we're not going to watch now, but if you want basically a step-by-step, here's every single thing you need to do for phase 3 of the project, this video will do it for you. So if you just search my YouTube channel for sizing a reservoir demo, then it's all right there. It explains column by column what you need to do to figure out how big the reservoir should be. And an important part of that demo, I think I emphasized the point during the demo, but I'll mention it again. This data has midnight at the top of the list, but you need to reorder the data so that the first hour that's included in your calculations is when the reservoir starts to fill in a 24-hour cycle. So if you look, it's not midnight that the reservoir starts to fill. The reservoir starts to fill before midnight. So just maybe put a little note to yourself that when you are doing your reservoir sizing, you need to reorder the data so that the first hour is that hour when the reservoir begins to fill. All right. So any questions before I turn you loose to watch that video sometime after class? Any questions about the purpose of the reservoir? The basic concept is we want to know hour by hour how much water is in the reservoir. And then you know how big the tank needs to be built. If you give yourself maybe a 25% safety factor, if you calculate the overall volume of water that's largest during the daily cycle, and then you make your reservoir 1.25 times that volume, then that's a good margin of safety for sizing the reservoir. All right, so back to open channel flow. When we first started talking about open channel flow, we talked about steady, uniform flow. And what formula do we use to determine the flow depth when conditions are steady and uniform? Manning's equation. Oh, thank goodness somebody got it. I was like seeing my whole life flash before my eyes. Yes, Manning's equation. That's when steady and uniform conditions apply. Otherwise, which is to say most of the time in the real world, there's going to be some sort of a disturbance that interrupts steady and uniform flow, so that we have to figure out what will be the flow depth after some sort of an irregularity, like a change in slope, or narrowing of the channel, or an expansion of the channel, or a step up or a step down. Just think about water flowing through a river does all sorts of irregular things. It's only prismatic channels that are engineered where we're likely to see Manning's equation over any kind of a long distance. Maybe we'd see Manning's equation over a short distance in open channel flow that's natural. In any case, we're using specific energy equation. This is the one where we've been solving cubic equations and trying to figure out which of the two positive roots represents our new downstream depth. So the idea of the specific energy equation is we look at the specific energy upstream and we say that the specific energy downstream is the same unless we have an expansion or contraction when a coefficient is provided. And we'll look at one of those cases today with an example. But here's just kind of the overhead view of the specific energy equation, is that specific energy measures the amount of energy in the water above the bottom of the channel. So it's not total energy. Total energy would include a delta Z term. But specific energy just looks at how much energy is there in the form of depth and velocity head. And so these three equations are equal. It's just, are we expressing the velocity head in terms of V, in terms of large Q, in terms of lowercase q? And there's different times that we'd use different equations. And in fact, we could mix and match. We could use the left-hand side of this equation and the right-hand side of this equation interchangeably, just so long as we're calculating the specific energy at 1 and setting it equal to the specific energy at 2. So we briefly talked about contractions on Friday. That's when we've got water flowing through a channel, but the channel gets narrower. And what happens when there's a contraction is that the same flow rate, Q, large Q, is flowing through a narrower channel, so the flow per unit width, lowercase q, increases. Because flow per unit width, remember, lowercase q, is big Q divided by the width of the channel. So if the width of the channel is smaller, then flow per unit width is bigger. So remember that when conditions are critical, that's associated with the minimum specific energy. And so one of the easy ways for a rectangular channel that we can calculate the minimum specific energy that's required to avoid choking is just to multiply the critical depth by 3/2. So a specific energy diagram is a representation of some combination of flow depths and velocities that convey the same flow rate Q through a channel of given geometry. And so like here is on the left side, this is the specific energy diagram for the flow at 1. And so at 1 there was some velocity, some specific energy that's minimized, and that's the critical depth. And if you make the channel narrower, then lowercase q is bigger, so that means the critical depth is larger. So there's going to be some larger critical depth, and with that associated with a larger specific energy. So when you make the channel narrower or wider, you're moving the specific energy diagram either to the right or to the left, and you're translating it up or down. So here, if you make the channel narrower, you're meaning that there's a larger critical depth and a larger minimum specific energy. When it expands, then the opposite is true. You now have the same flow rate, Q, but going through a bigger B. So if B, the width of the channel is larger, then that means the flow per unit width is less. So if the flow per unit width is less, then that means that the critical depth is less. So how will it be shifted vertically? Well, if the flow per unit width is decreased, then the critical depth is decreased, and the specific energy is also decreased. So it's shifted to the left. So vertically lower, horizontally to the left when the channel expands. So that means that the minimum specific energy is lower than it was before when the channel gets wider. So this is something that I gave you a preview on to, like, as one of the homework help type hints. And this loss coefficient allows us to account for turbulence and flow irregularities that occur when a channel gets narrower or wider. And it subtracts out some of the specific energy so that it's no longer available at 2. So that's going to mean that some of the energy that was originally present at location 1 is basically burned in the process of setting up a new channel width. So if we're accounting for those losses, then you'd simply add it to the right-hand side of the equation, because the specific energy formula is directional. We assume that water is always flowing from 1 towards 2. 1 is the upstream location, 2 is the downstream location. So if we're accounting for losses, then those losses need to be lumped in on the right-hand side of the equation so that the energy that was previously at 1 is now gone and not included in the specific energy terms for location 2. All right, so let's put some specific numbers into this. Now, this is really counterintuitive, and I addressed this last week when I said, so you've got water flowing around at location 1. The water is 2.75 meters. So we've got a certain flow rate here. It says 9.9 cubic meters per second. We know the width of the channel is 3 meters. Now, if the channel's getting wider, maybe you just instinctively think that the water is going to get shallower. You know, if this was just like a tank of water, if you made the tank have a larger top view area, then the depth of the water in the tank would become shallower because it's a fixed volume of water. But that's not what's happening here. This channel is getting wider, and we don't know, without doing the calculations, we don't know if the water is going to be deeper at 2 or shallower at 2. It's very counterintuitive, and we can only rely on the calculations. There's nothing from just kind of an instinctive level that we're going to know before we, number 1, assess the flow regime, and also, number 2, account for the losses that are occurring in the transition here. So we have a C factor provided. That implies that we shouldn't neglect the energy loss due to the expansion. So let's go through these calculations and find out what will be the new flow depth downstream if the channel is going from a width of 3 meters now to a width of 5.7 meters. Okay, so here's the specific energy equation, where on the right-hand side of the equation we've got this energy loss term. And I've summarized the steps that I suggest you follow here. First of all, calculate the flow per unit width at 1. From that, because this is a rectangular channel, we can use this simplified approach to find the critical depth at 1. And then part C says to compare the flow depth to the critical depth, because that's an easy way for us to determine the flow regime, which is to say whether conditions are subcritical or supercritical. Then calculate the flow per unit width at 2 and substitute everything into this equation at the bottom. All right, so I'm going to pause the recording. I'll also be doing these same calculations over on the whiteboard if you want to double check your own calculations. And let's find out, what's the water doing? Is it getting shallower or is it getting deeper because the channel got wider? Okay, the water's flowing around through a channel that's 3 meters wide. It expands to 5.7 meters in width. So here's the step-by-step process that we're going to follow. The flow per unit width at location 1 is 3.3. We can use this abbreviated method for finding the critical depth because the channel's rectangular. If your channel's not rectangular, then don't use this. You'd have to use the full Froude number equation to find out what's the critical depth. But we can use it. The critical depth's 1.035. Now, if the given flow depth, which we're told is 2.75 meters, if the given flow depth is larger than the critical depth, that means we have subcritical conditions, because subcritical is slow-moving water, and if the flow depth is larger than the critical depth, that means that the velocity of the flow is going to be relatively slow-moving. So subcritical at 1. We'll file that in the back of our minds for later. Then we need to find the flow per unit width downstream after the channel has gotten wider. So we now know the flow per unit width at 2 is 1.737 meters squared per second. So then here's the specific energy equation when we are accounting for the expansion loss. Now I could have just said 1 plus c and multiplied it by this. You know how it's 0.45 times the velocity head, and this is 1 times the velocity head. So maybe I could have just said 1.45 times the velocity head. But in any case, what we've got is the makings of a cubic equation. The left-hand side is a constant because we know the velocity head and the depth upstream is 2.823 meters. And then downstream there's going to be the depth and the velocity head, where I've now combined together. There's an unknown depth in both the energy loss coefficient and the velocity head. So if we rearrange the specific energy diagram, multiply each term by y2 squared, then this one becomes y2 cubed, this becomes y2 squared, this becomes just a constant, and we reject the negative root. We don't have supercritical conditions, and so the supercritical root we reject, and the new flow depth after the channel gets wider is 2.79 meters. And so the original depth was 2.75, and it lost quite a bit of energy because of the expansion. And despite that, despite losing all of that energy because of the expansion, the flow depth is still larger downstream. So that's what happens when we have a different flow per unit width and also account for energy loss through the transition. Does anybody have any questions about that approach? We can use the same method if the channel gets narrower. So, here, if we didn't know the flow depth after the channel gets narrower, it would be the exact same process. This example, I'm asking a slightly different question. In this example, I'm saying, so the scenario is we know everything at 1 before the channel gets narrower. We know the width of the channel from the depth and velocity. That defines the flow rate, because if we know the width and the depth, that's the cross-sectional area, A, and then A times V gives us Q. So we effectively know how much specific energy there is at 1. But this example asks, what if we kept making the channel narrower and narrower? Eventually, we'll get to the point where it's so narrow it's going to choke the flow. Like there's an upper limit to how narrow it can be. The same isn't true, by the way, of an expansion. There's no expansion width where you make it so wide and suddenly it chokes the flow upstream. Because remember, the purpose of choking is to accumulate energy when there's not enough specific energy at 1 to overcome some obstruction. So a channel getting wider, it's not an obstruction. But a channel getting narrower potentially is an obstruction. And so the way for us to analyze this, if we want to know, what's the minimum width we could have downstream at 2 and avoid choking. So what we'll do is we'll just assume that the conditions are choking at B, so we'll let the depth be the critical depth. So just before choking, the conditions are critical at location 2. So what we know for the critical conditions is that's associated with the minimum specific energy. So we'll say, let's assume that the minimum specific energy at 2 is equal to however much specific energy was available at 1. So we'll just, with the data that we've been given, calculate the specific energy at 1, and then set that equal to the specific energy at 2, and solve for the critical depth using the notion that critical depth is 2/3 of the minimum specific energy. And then once we know what is the critical depth associated with that minimum specific energy, then we can calculate all the flow parameters. And so let me just illustrate this one for you. If the channel is getting narrower, then the smallest allowable B is going to lead to the largest allowable flow per unit width prior to choking. So remember, the minimum specific energy is the most efficient energy associated for a given flow rate. It's the least amount of specific energy that allows you to convey the flow without choking upstream. So if I calculate the how much specific energy there is at 1, it's just the flow depth and the velocity head, then 5.14 feet is how much specific energy there was at 1. And so I'm saying, what would be the critical depth if we had 5.14 feet of energy available? So just the critical depth is 2/3 that. This velocity head would represent 1/3 of the minimum specific energy. So the critical depth would be, it would be flowing at the critical depth just before choking. This is the critical depth it would be flowing at. And since the critical depth is 2/3 of the specific energy, the remaining energy would be equal to the velocity head. So we can solve for the velocity. And for a given flow rate, we can find the cross-sectional area. And therefore the maximum, or the minimum width prior to choking. So if we made the channel any narrower than 4.17 feet, then the flow per unit width would be too high, and we wouldn't be able to accommodate the flow for the minimum specific energy that we have available. Because there's just, when the water is flowing at 1, there's only so much energy associated with that. And as you make the channel narrower and narrower, it's requiring the water to flow at a higher velocity to get through that obstruction. And eventually you'll run out of energy. There won't be enough energy to accelerate the velocity to what it needs to flow at through that very narrow channel. That's why it will begin to choke at 1 if you make it any narrower. So 4.17 feet is the minimum width. This is a lot of if-then. I mean, we're like several steps deep into the if-then, and you know, like, this is the sort of thing where I think it would be worth your time to think about it again this evening. Give it another look and try and think through, like, why is it that making it even more narrow would cause choking in the flow? So consider it from the standpoint of specific energy. Now, making the channel narrower is not the only way that the cross-sectional area of flow would decrease. You would also decrease the cross-sectional area of flow if you have piers. So look at this bridge. You can see that the piers are down in the river, and so the effective flow area through the piers is less than the flow width upstream. So the water's flowing from this direction towards the piers. You can tell just visually. But the question is, when the water goes through there, will the water level rise or will it fall at the constriction? Like, will the fact that we have less flow area cause the water to be higher or lower in the vicinity of those piers? And the answer is, we don't know until we do the calculations to determine whether the flow conditions were supercritical or subcritical, and then if we know some sort of an expansion or contraction coefficient, what's the effect of the losses? So when the channel is changing width, we have to consider that there's a new specific energy diagram. And if the channel is getting narrower, That means the flow per unit width is increasing, and then that is pushing the specific energy diagram to the right and higher. So the flow per unit width is increasing when the channel is contracting, meaning getting narrower, or if there are some obstructions in the channel that constrict the flow through less effective flow area. Contraction and constriction, they mean effectively the same thing, just that B is less. The width of the channel is less, so therefore the flow per unit width is higher. So if the flow per unit width is higher, then the critical depth is higher, which means the minimum specific energy is higher. So it gives us a whole new specific energy diagram. But then whether the depth is increasing or decreasing depends on, whether you are in the subcritical route, which is up here, or the supercritical route, and then whether you're accounting for losses. So let's consider this pier. That upstream we knew the width of the channel, we knew the depth of the flow, we knew the flow rate, but then we're building a bridge over the channel, and it necessitates us putting in a couple of piers that are each 0.25 meters wide. So that means if each of these is 0.25 meters wide, then upstream the width of the channel was 2.5 meters, but then downstream the water is only flowing through a width of 2 meters. So will the water be deeper or narrower because of that constriction? Well, what we'll do in this example is just assume that there are no head losses, that there's no expansion or contraction coefficient that we'll be keeping track of. And so the steps are to find the velocity at 1 and the specific energy at 1, and then set the specific energy at 1 equal to the specific energy at 2, where the new flow per unit width is going to be higher. Because the width is lower, the flow per unit width is higher. So let me pause for a second and see if you could just reason through, like, what's the calculation methodology that you need to follow here to find Y2? All right, some more. Okay, so the channel is effectively getting narrower. So it's the same as if, if the B is decreasing because of a contraction in the width of the channel or a constriction like this pair of piers that it's going in, the net result is the same. The flow per unit width goes down. So just to start things off, we could find the specific energy at 1. It's the depth and the velocity head. The water's flowing at 1 meter per second with the given 2.25 cubic meters per second and the given flow depth of 0.9 meters. So we find the specific energy at 1, and we're going to let that equal the specific energy at 2. Remember, we're neglecting any losses here through the constriction. And so if the specific energy at 1 is equal to the depth and velocity head at 2, the only unknown here is Y2. And we find the cubic equation, and there are 3 routes. The negative one, which we reject, a supercritical route, and a subcritical route. Well, there's a couple of ways we can assess whether we should choose the supercritical or the subcritical. One would be just to find out what was the critical depth before the constriction. So the critical depth before the constriction was 0.436 meters, and the actual flow depth was 0.9. So that means that if Y1 is greater than YC, then that means subcritical flow. The other is that we could calculate the Froude number at 1 and assess the flow regime that way. And so the Froude number at 1 is 0.337. So that also confirms that at 1 the conditions were subcritical. So we should select this flow depth. The new depth after the constriction is going to be 0.865. So it's counterintuitive that sometimes the water is going to get deeper, sometimes it's going to get shallower. It depends on the losses, it depends on the flow regime, but here we got that the new flow depth would be 0.865 meters. Oh, I've kept you a minute over. Shoot, I hate it when I do that. I'll pay you back, I promise, one of these days. Homework 10 is due before class on Friday. We'll have an exam on Friday. And yeah, let me know if you've got any questions as you're working through the homework assignment.